Okay, so in this video, let's put the technology that we've talked about, namely flash SSD devices, into a specific context where I'll be talking about some technology optimization techniques that can be used to walk around the inherent limitations of a typical flash device. And what is that limitation? The limitation is specifically the asymmetric write operations, right? Because Flash doesn't support overwrite. So in order for the write intensive operation, for write intensive workloads, it might incur significant overhead just for the Flash to erase all the Flash pages, all the Flash blocks before it can accept the new write operations. And this is an inherent limitation. And without optimization or workaround solution to kind of eliminate this kind of limitation, it would dramatically impact the performance of the runtime, the application runtimes. Okay, so in this video, let's see how Flash can be used to be working with a file system application in an efficient manner. So the file system topic, we'll be talking about file system topic in our last lecture in next week. But before that, we'll be just using this file system as a high-level application to try to motivate this specific optimization technique that we'll be talking about in the context of flash devices, okay? So traditional file system, it's used to support traditional spinning mechanical hard disk drive. And recall that for a hard disk drive, its operation model is relatively straightforward, right? It only supports traditional read and write APIs, which are read sector and write sector, or read disk block or write disk block. Okay, so what are the problems if you want to port a traditional file system application for it to work with a different types of underlying storage device, which is not hard disk drive, but flash device, right? So because there's a mismatch, there's inherent mismatch. If here we're talking about flash instead of hard disk drive, and flash supports this program write and also erase write operations, okay? And these two doesn't match this basic write sector interface that was originally used to support traditional hard disk drive based file systems, okay? Let's further zoom in and see how exactly this hurt the performance. So before that, let's first go through this, how to naively port this traditional hard disk drive interfaced file system so as to make it support the Flash APIs. So the straightforward solution is to write a wrapper which wrap around, which wrap around this Flash APIs to be able to expose the file system, the basic hard disk drive based file system APIs, which are read and write sectors. But within the definition of read and write operations, it embeds and wrap around the Flash APIs, the Flash read, and those two write APIs, namely a program and erase, okay? Flash read and erase and program. So let's go through the steps one by one. So first, let's take a look at the read operation. Read operation is relatively straightforward, right? Because in both hard disk drive and flash devices, these two devices, it supports same kind of read APIs, which is read sector or read block. In the context of flash, it is read flash page, okay, which is kind of like read disk sectors. So for read, it's relatively trivial. But the difficulty lies into the write operations. Okay, so let's see why write is trickier compared to read operations. So in order to support a flash, in order to support a hard disk friendly file system semantics, we need to wrap around the asymmetric flash write operations therein, right? So how to do that is we first perform a really coarse-grained, costly flash read, which is, so the parameter of this flash read is, it takes the parameter as all the pages of a flash block. It basically reads the whole flash block out from the disk, or from the flash, into the memory, and makes an in-memory copy, which is called the block copy. Okay, and in order to support in place, in situ update or overwrite operations, you can just freely do so by modifying this in-memory chunk, in-memory block copy of the data with the new data. Okay, you can freely do so because here we're talking about in-memory data or in-memory state. Okay, so this is within memory. Okay, and the third step, so this is the first step. Second step. Third step is you want to write this newly updated in-memory copy all the way down to the flash disk, the flash drive, right? So recall that you cannot do so directly because flash doesn't inherently support overwrite. In order to do so, you need to first conduct a whole block erase operations. So this is the whole block, the targeted address of the block, a flash erase, and then followed by step number 4, which is the flash program, which is a finer grained program operations. And the parameter of the program operations is obviously all pages of this particular block, right? So what are the most severe issue of this seemingly workable, working protocol, right? What are the issues? So the issues are, let's say you want to just update one single digit or one single flash page within this hundreds of flash pages within this block. You have to read all the data out from the disk into the memory, which consumes memory, and just update that one of the hundreds of flash pages within the memory, and then perform a whole flash block erase, even though you only target one single page out of the hundreds of them. And then perform the flash program on top of all the pages within the disk device, within the flash device. So this is so costly because you carry over too much overhead in order to just work with just a small subset of all the data that you want to carry over. So this is obviously too costly. So put it in a more specific context, let's see why this example is bad, why it incurs just too much runtime overhead. Okay, so let's see how this awkward flash write gets implemented. So it has 2 different levels of storage. The top level is the memory, and the bottom level is a flash. So in this case, we have 3 different flash blocks, and each flash block holds a total number of 4 flash pages: page 0, page 1, page 2, page 3. Okay, and the same thing for block 1 and block 2. So let's say the user requests or the file system request to write something new into the address that belongs to block number 0, and also more specifically belongs to page 0 of block 0. So it writes something new, which is 0001. Okay. So how to do so? Recall that walk around the protocol, write protocol, is you want to read this whole block out from flash into the memory, right? And then perform the fine-grained update. So the first step, read this whole block out into the memory, which typically consume a lot of memory, which is not necessary, right? And then the second step is just perform this fine-grained update, which only target the very first page, 0, right? Recall that the new data is 0001. So you just flip the fourth 0 into 1, okay? So the next step, perform this fine-grained update, modify the target page in memory. And then third step, what is the third step? The third step is you want to perform a whole block erase operation because it doesn't support overwrite. No overwrite, so you need to erase this whole block 0. Erase it, basically flip all the 0 back to 1s. Even though these data, page 1, page 2, and page 3, they are fine. They have not been touched. You have to erase this whole data again, right? Okay, flat it all by 0, flat it all by 1. Erase this whole block. And then the last step is write this data by performing a large program operation. Write this whole data in memory data into the flash device called program. Okay, so this is the fourth step. But the only thing that gets updated is only page number 0 within block number 0. Page 1, page 2, page 3, they are staying the same. But these are the overhead that you have to carry over all the way from memory to the disk, from disk to the memory, from flash to the memory, from memory to the flash, right? So the issue is called, there's significant write amplification, right? And here we're talking about random small writes. And because of this write amplification issue, random writes are particularly expensive for flash devices. And the root reason is because flash only supports this asymmetric write operations. It doesn't support overwrite. And writing one 4 KB flash page may cause this whole series of really costly operations, which is read, erase, and program this whole 256 kilobytes of flash block, assuming the granularity of the flash block is 256 kilobyte. So the write amplification factor in this case is 256 kilobytes divided by 4 KB is 64 times. This is extremely high, right? So random writes are extremely expensive for this naively designed software that is, seemingly working for the flash device, but not working efficiently. That is why we introduced this technique, which is called FTL, which is a short of flash translation layer, which is a new abstraction that basically adds up one more abstraction layer to perform one more level of translation so as to convert all the random IOs into sequential append IOs, sequential appends, by adding one more abstraction layer. Okay? Sometimes in computer science world, by introducing one more abstraction layer, it can be used to more efficiently solve a hard problem. And in this case, we introduce this flash translation layer. Okay. So this flash translation layer is added between the upper level file system and the lower level flash, but inherently it's part of the flash hardware device. Its responsibility, it is responsible for translating this logical device address, or LDA, into the physical address. So this is kind of, so this similar to the functionality of a in-memory page table. Right? Recall that how to support memory virtualization is by introducing a page table, which is an indexing data structure that is responsible for facilitating the address translation from the virtual page address to the physical frame address. Okay? So that way support memory virtualization. So in the context of a flash device, by introducing FTL, it could be used to support so-called flash virtualization. By introducing one more abstraction, which is a logical address space abstraction, okay? So that its ultimate goal is to convert in-place write into the append-only writes, which is supported more efficiently in the context of flash device, okay? Let's see how it works. Here in this example, I draw this separated logical layer and the physical layer. So this logical layer is the flash translation layer, which is, used to maintain this logical address to the physical address mapping. So here, this is logical address. And this logic address table gets mapped to the physical address space. Okay. In this example, logical address 0 gets mapped to the first page, which is page 0 of block 0. Page 0, page 1. Logical page 1 gets mapped to physical page 1. And logical page 2 gets mapped to physical page 3. And logical page 3 gets to map to physical frame 4, and so on and so forth. Okay? Let's see, given the existence, by introducing logical flash translation layer FTL, how this random writes gets more efficiently supported. In this example, at a certain point of time, the application or the file system want to write 0011, a new data into the physical page number 1, okay? Physical page number. Physical page number 1, which gets mapped to the logical page number 1 as well. So how it does is the flash translation layer tries to identify a free block. So it tries to identify, in this case, it identifies, page 4 and page 5, which is physical page 5. And it redirects this new write to this page, which flips the first ones into 0. And then invalidate this mapping and mark this page as invalid, because it holds the stale or old data, which is subject to garbage collection. Okay, and flash device often supports garbage collections operations. Okay, so this is how it works. Let's go through the animation. So it identifies this and write this new data into this, which is page number 5. And then it changed the mapping. So the logical address number 1 gets mapped to physical address number 5, which belongs to the second page under physical block number 1. Okay, change the address mapping. This is the second important step. And then the third step is you mark this physical page number 1 as invalid. Okay, as invalid. And this is subject to garbage collection, later phase. If you want to reuse this whole block, you need to garbage collect the data for whatever useful data, which holds useful user data. In this case, page 0 and page 3. They are used to hold data. Needs to be forwarded to a new place. For those data that marked as invalid, for example, this page 1, is subject to be garbage collected. To be erased completely. Okay. So this is a bird's eye view of solid state drive architecture with the support of flash translation layer, or FTL. Okay. So FTL exposes the disk-like interfaces, which is read sector and write sector. Exposes interfaces, and internally, it's responsible for dynamic address translation. Just like a page table for supporting memory virtualization. And all this mapping relationship. But unlike page table, which is stored similar to page table, which is stored in memory, the FTL mapping table is stored in SRAM. Okay, it's stored in SRAM. So SRAM is a small piece of dynamically allocate, a small piece of extremely fast memory device, which could be used to, store data structures or runtime state. In this case, this mapping table indexing data structure gets stored within SRAM, which is part of the hardware that belongs to this flash. So this is the whole flash. And then these are banks, blocks, and pages hierarchy. Okay. So again, the flash translation layer is a piece of firmware which is often implemented in flash devices firmware. And where to store the mapping? Again, it stores in SRAM. And again, these physical pages within the flash device can be within either one of these 3 different states: valid state, invalid state, and free state. Let's see how these 3 different states how the operations transit the state from one state to another, transit the block from one page from one state to another. Okay, so if you perform an erase, right, you basically flip all 0 back to 1s, so that all the pages within a typical flash block starts with the free state. It holds all 1s, okay? And then you write something, which is program. You program zeros to any one of these multiple pages that belongs to this flash block. The flash device transit the state of this particular page from the free state into the valid state, okay? Right now, it gets marked as valid, meaning it is used to hold meaningful user data. Meaningful data. And if there's an overwrite, meaning you want to overwrite something to this valid data, to the valid page, the flash transit the state of this particular page from valid to invalid. Okay? And again, as mentioned in the previous slide, the invalid pages are subject to be erased, right? And because this override will append the new state somewhere else. And this identifying somewhere else, try to locate some free page somewhere within the flash device, is the responsibility of FTL. Okay? And let's say FTL, the flash regularly runs garbage collection operations. Okay? And it tries to, during the garbage collection operations, and it tries to erase this whole flash block in a coarse granularity. Erase basically all ones. And this transit the state from invalid to the free if there's any invalid blocks, pages within this block. Okay, so this is how, you know, the states gets transited from one to another in terms of this physical pages within a flash device. Okay.